My name is Cheng-Wei. I work with Stevanović at Colorado Mines and National Renewable Energy Lab. Today, I'm going to talk about our recent work on computational search for novel silicon qubits. So here, I would like to motivate our work by comparing three classic semiconductor qubits. We have NV-centered in diamond, phosphor in silicon, and silicon spin-based gate control silicon nano structure. For NV-centered in diamonds, it's known to be able to operate at up to room temperature, making it good for quantum simulations. For quantum sensing. And its natural spin-photon interface also make it good for quantum communications. On the other hand, for spin-based qubits, it generally requires a low operating temperature, but its long coherence time make them good for quantum computing and quantum computing. For the silicon nanostructures, since it has potential to have a well-defined repeating structure, it is also good for quantum simulations, and therefore it has good potential scalabilities. Scalability is one of the biggest challenge for semiconductor qubits, and NV-centered in diamonds and phosphor in silicon has limited scalability due to its stochastic nature of how the defect is created. Here we are interested in silicon because it has the better potential to integrate with current silicon-based classical devices. However, it's known that it doesn't have well-established spin-photon interface and require low temperatures. So in order to address this, we conduct a computational search for NV-center-like deep defects in silicon, which can potentially serve as spin-photon interfaces and hopefully operate at higher temperature. Here we specifically look at transition metals because there are known deep defects in silicon. So before we talk about the general workflow, we need to look at the NV-center first. NV-center in diamond first. It's well studied and known that it has triply transitions within the bandgap, and its specific inter-system crossing make the room temperature operation possible. So as the first step, here we are searching for transition metals that have triply transitions within the silicon bandgap. And here's our computational workflow. We look at 14 transition metals at interstitial size, substitutional size, and the vacancy complexes. We start with point defect calculations that based on hybrid functional and supercell approach. With that, we can have charge transition levels and defect level diagrams. We know that we need to have at least 2 transition levels for the silicon bandgap to accommodate triply transitions. We also look at a defect level diagram to make sure we have the defect system can have the spin triply ground and excited states. At the end, we need to make sure those transitions are allowed. With this workflow, we identify 9 candidate transition metal defects. So here, let me use the substitutional transition metal defects as example to illustrate our workflow. We first look at the charge transition level. Y-axis is the Fermi energy. Now, those signs indicate the stable charge states at a given Fermi energy. Now, applying the criteria of at least 2 transition levels, we identified scandium, cobalt, nickel, copper, zinc, platinum, and gold as possible candidates. But since charge transition level doesn't have direct information about the spin configuration, now let us look at the defect level diagram. Here we use neutral zinc substitutional defects as example. Y-axis is the Fermi energy. We have 3 up spins compensated by 1 down spin, and 2 unpaired electrons make it a triply ground state. Here we also make sure those states are localized defects, shown by their spin charge densities. Next, we need to make sure those transitions are allowed. To do so, we look at the absorption coefficient for the substitutional defects. And for these transitions, for this transition, we find that it is pretty bright. at the order of 10 to the power 4 per centimeter. So that means these transitions are optically allowed. We also see that they are far away from other transitions. So there's a distinct peak. So using this workflow, we identify 9 candidate transition metals. We identify 5 substitutional defects with specific charge states and 4 interstitial defects. However, unlike other wide bandgap tetrahedrally bounded host materials, we don't find any vacancy complex. So now here we organize our results using periodic table, and we can clearly see that the interstitial defects are located at the left end of the periodic table, while the substitutional defects are located at the right end of the periodic table. They also have very specific charge states to have a triply transition within the bandgap. Now the question is why? Oops, chat. Okay, oops, sorry. So in order to understand this, we look at the electron counting and projected dose. To start with, we look at the, we know that the minimum requirement to have a triplet ground state is to have 2 or 4 electrons within the bandgap. Now, looking at the electron counting for substitutional defects, we know that there will be 4 electrons from the silicon dangling bounds. The dangling bounds also contribute to 4 in-gap states. Now, if we take as neutral zinc substitutional defects as example, the zinc contribute 12 valence electrons. So now we have 16 electrons we need to accommodate when the zinc substitutional defects are created. To help the process, we look at the projected dose for the substitutional defects. Shown here, the shady area are the bulk silicon dose. And we have the d orbital here, s orbital, and p orbital for transition metals. And this trend is generally the same for the transition metals. And what we see here is we clearly see that the d orbital and s orbitals are below the valence band maximum. That means for those 16 electrons, the 12 of them will go to fill those 4s and 3d orbitals of the transition metals. And then we have remaining 4 electrons, and they can go to in-gap states. So now, in order to have a 2 of 4 or 2 electrons within a bandgap, that means the zinc substitutional defect needs to have the charge state of 0 or +2. This approach can be generalized for different transition metal columns. And so, moving to the left of the transition periodic table, we find that the charge state the required charge state become more negative and negative. And at some point, it becomes too negative for the charge state to be stable within the silicon bandgap. And that's the reason why substitutional defects are located at the right end of the periodic table. Same approach can be also used to explain why interstitials are located at the left end. With that, I'd like to summarize. Here, we identify 9 candidate defect systems out of 14 transition metal elements. These candidates can potentially serve as spin photon interface and potentially operate at higher temperature. Here, we also discovered the general trend for candidate defects regarding their charge states and their defect sites. Also, our results support the concept of portable transition metals. So, for example, the vanadium is also a color center in silicon carbide. And this also suggests that the candidate identified here can be potentially as potentially color centers in other tetrahedrally bounding host materials. As our future work, we plan to look at zero field splitting, hyperfine parameters, zero fault lines, and intersystem crossing to make sure those candidates can operate similarly to the NV center in diamonds. And we're also looking for experimental realizations.